into the content here. So fire, right? It's sort of like the obvious topic that any reasonable forest ecology, forestry, or woody plant biology course in the Western US and many other parts of the world has to confront. It's such an ever-present management issue that it affects all kinds of aspects of our lives, and often in ways that are very unpleasant, from the hazards, the health hazards that are associated with smoke pollution, to the risks of combating wildfires that if you're going into the fire service, and I know that some of you are interested in that you will face, and also the risks to property and lives and property. Many of our towns and cities, if it wasn't already clear, we've learned the hard way in the last decade, they are at risk to these kinds of events. As I say, fire is a process, a landscape level process that shapes so much of how Western forest ecosystems work. We have to think about it. We have to at least acknowledge its presence if we're going to be effective in any way. So this is a picture of the Soberanes fire in 2016. It was a fire in Big Sur. Let's see here. Besides the fires themselves, one of the effects of fire are something that you see everywhere you look in the Central Coast and really in broadly in the West. In the species that dominate our forests themselves, you can see the effect of fire even when there's no evidence of it having occurred. And what I'm talking about is an evolutionary effect. There is lots and lots of adaptation, prevalent adaptation to fire. So individual adaptations like resprouting, which is like what I'm showing here, it's a very common and probably one of the most common adaptations to persisting in coastal California. We actually have quite a lot of broadleaf dominant forests in coastal California, and lots of broadleaf trees are able to resprout from the basally, and that helps the individual persist through fire, even though most of the biomass may have been killed, most of the above ground biomass. And so this is tan oak here, but when you look across our forests, every major species in coastal California, every major species in our coastal forest except for one resprout. So our broadleaf plants resprout, tan oak, our oaks, madrone, bay laurel, even some of our conifers resprout, and that's redwood. Resprouts prolifically after fire. So what's the one coastal forest dominant that doesn't resprout?
Douglas fir.
There, bam! Yes, that's right. And Douglas fir actually, if it's big enough and old enough, the bark is thick enough that it'll persist through fire, yeah, so it can be fire resilient in some circumstances too. So this is just, I got a couple examples of this, but it's just really to make the point that you can have devastating fire, fires that kill most of the above ground biomass, but actually kill very few individuals. So this is adaptation in Central Coast. Most of the individual trees in this photograph are alive, but they've lost 100% of their above ground biomass. And that's just life in Central California. It burns, especially like this is in Big Sur. It burns. When it burns hot. It burns like chaparral, burns really hot. And this species remarkably are able to persist, but they do it through below ground structures and resprouting. And this is another example. This is black oak, also in Big Sur. And what you're seeing here is these individuals are all resprouting, but in this case, they're resprouting epicormically, so they're resprouting in the canopy. In this case, the stems are actually still alive. They survive the fire, and then it's just going to refoliate, which is another strategy. And it's just, this one's just was really kind of blew me away that it was so prolific. So of course, this is an important way that you kind of reestablish canopy cover quickly, and that can be helpful for a lot of reasons. But that's not the only way that species will persist through fire, and bishop pine and Monterey pine are good examples of serotiny. And these are cones, these are all closed cone conifers. And serotiny is a mechanism for seed bank persistence through fire. So those closed cones, oftentimes things like knobcone pine, they're fused shut with resin or just closed pretty tightly. And the cones will expand when they're heated in fire. So what this ends up doing is it creates a protective, kind of protective house or whatever structure for seeds during a fire, and then after they're heated up, the seeds are then spread. So forests like bishop pine, Monterey pine, and in the Sierra Nevada are lodgepole pine. Those cones are closed, and they rely on fire for actually germination and renewal. This is Point Reyes after the Vision Fire, which was 2000 something, early 2000s, I believe. And this is just post-fire regeneration. I just like to show this photo because it just shows just how dense this can be. Prolific regeneration after that fire. And the other way that plants or woody plants or trees get through fire is to avoid it in the first place. And we have lots of examples of this. It's less dominant in the Central Coast, but many forests, for example, in our riparian forest, those species, essentially the strategy there is to avoid fire altogether. They're growing in wet areas that are cooler, that generally are going to, they're going to burn less often, and when they burn, they're going to burn cooler. So the individuals are just more, it's just easier to persist. But there are other examples of avoidance. This one was kind of interesting. I haven't been here, but this is a paper I found that was in the Gibson Desert in Australia. Fire structures this landscape. When it burns, that shifts dominance towards grasses, but then over time, it's wet enough, and then woody plants will move in and establish in those grasslands. So what you have here is kind of like a constant shift between woody vegetation and grassland, and a lot of it's driven by fire. Anyway, just pretty cool. The landscape is in a constant state of flux, even though it's stable in a way. It's a dynamic stability driven by fire. Okay, and so my guess is that you're biased in the same way that I was when I was an undergraduate in a Western university. And I thought I left my undergraduate days feeling that fire was the most important factor structuring forests anywhere in the world. And one of the best things that happened to me was that I went to the University of Maine to do a master's degree. And I realized when I got there that fire is kind of a fluke. These are really wet forests. They're frozen solid for a lot of the year. And even in the summer when it's hot, they're just wet. I mean, it just rains a lot, and you're doing like battle to the death with hordes of mosquitoes and these biting insects and stuff. I mean, it's like it it was not like the ponderosa pine ecosystems in northern Arizona. These places were wet. They wouldn't burn if you wanted them to. You go out there with a drip torch the size of a semi truck, and I mean, only under the most unusual circumstances can you get them to burn. For example, give you a sense here, the average burn return interval here is on the order of 500 to 2,000 years. It's a fluke when it burns. It's an absolute fluke. It's some sort of, I mean, every 2,000 years, what does that even mean? You know, that means that some weird confluence of events happened and there was some like epic drought, and then some fluke thing ignited the forest. I mean, it's so rare that the plants are not adapted to fire. There's really virtually no adaptation in these interior forests to fire. The exception that you get, and you may know about this, but on the weird thing about on the East Coast, as you get closer to the coast, and sometimes I'm talking about a very narrow band of forest along the coast, you'll actually get forests that are adapted to fire and where fire is pretty frequent. So occasionally it feels like once every 10 years there's some really destructive wildfire on Long Island that burns up, like a bunch of rich people's houses. Will she come? And that's an example of this kind of rare fire thing. You want to come say hi? Yeah. Come say hi. This paper that I assigned this week is just a great paper, and I know that it's 14 years old now. Much has been written about fire and fire in the West, but the basics of this analysis have stood the test of time. The patterns that they documented and the mechanisms that they are focused on it just really nicely sums up the situation that we're confronting. I mean, the big things here are that more frequent fires tend to be associated, in the mountains anyway, tend to be associated with the loss of snowpack. Hotter, drier summers and also hotter springs typically precede damaging wildfire. Now, that probably isn't surprising in and of itself, but it's really helpful and very convincing. Remember, we're in the business of using inference, empiricism, in order to figure out why problems are happening and what to do about them. This paper is showing pretty clearly that you can predict a bad wildfire season based on the snowpack levels and the temperatures in spring and summer. And that's really helpful. You think about these kinds of mitigation strategies that we're doing now, like shutting off the power in California, which is really expensive and really very dramatic intervention. Any kind of information about will we have to do this, that's really, really valuable. Oh, so, Hattie, yeah.
Quick question about the last slide.
Yeah.
When a rare fire does occur in, say, like a northeastern forest, how destructive is it, and how does all the plants as a whole respond?
Yeah, it's very disruptive, and it's not well studied because there's just not a lot of examples of it. There's always exceptions. There's places here and there that burn more regularly for whatever reason. They're just hotter and drier, relatively speaking. But in this case, this is like a swamp forest, and I don't know it ever having burned, and so it would, I think. But let me get away from that. What we would expect to happen here, if there's when there was a fire, should there be a fire, would be probably you know, something like a hurricane would probably be a better analogy for how it would affect forest structure. Reestablishment here and succession would probably follow something like that. But with these species, these spruce and fir species that dominate these forests, none of them have an advantage post-fire, not in particular. There's a little bit of white pine, this eastern white pine in these forests. It might have a slight, maybe have a slight advantage because of it benefits from scarified soil, from exposed mineral soil, but I feel like it's a stretch. It's so rare. It's like a, just kind of a fluke event.
As far as the fire traveling through, the temperature's not, you wouldn't expect it to get very hot just because of how saturated the understory is.
Yeah, I would not, I wouldn't. In particular, in these forests, it's this part of the world, that northern Maine is pretty flat and it's really wet. There are a lot of lakes and rivers, and just a lot of boggy forests. This is like really great habitat for moose, which like wet, boggy, forested terrain. And you'd have to have a very severe drought for that to dry out enough to carry a fire. However, what can happen, and this is in the case, especially in the western slopes of the Cascades, which you think about, which tend to be wet forests, but in occasional droughts, if they get dry enough to burn, they can burn. And the bad news is that they'll burn really, really damn hot, like scary. There's a lot of biomass in those western slopes of the Cascades. There's actually a lot of biomass in these forests too. And if it dried out enough, I wouldn't want to be around. They're dense, very dense forests.
So only in a case of severe drought in a forest like this would you get a fire that could actually spread and burn enough biomass.
That's right. Yeah. And I can't really do it justice with these photographs, but this thing's like a swamp. It was wet work, very poorly drained soil, standing water, sphagnum moss. It's this kind of wetland associate, it creates this like spongy forest floor that's like a foot deep sometimes. They were great forests. It's amazing. They grow a lot of timber and a lot of fiber. And it's an expansive wilderness in the Northeast. It's got a lot of roads in it, but it's different than Western wilderness, but it's still got definitely a wilderness feel. It's a different kind of place. I moved to the Northeast. I didn't realize so much of it was going to be a swamp. There's a lot of swamp in Maine. There's a lot of moose too. Anybody seen a moose? Cool. Big animal, right? Yeah. Yeah, respect that animal. It's like the size of a horse. So yeah, these authors were able to show, that the fire season is increasing with these changes in the temperature and snow melt dynamic or snow pack dynamics. And I thought that this was really helpful. It's one of the most helpful things to kind of look at. I feel like it pulls together a number of themes that we've talked about so far. Climate change is not increasing fire frequency everywhere, but it is increasing the frequency of very large fires. And they have this figure in the paper, which is showing this average wildfire frequency, and they're talking about big wildfires. with early snowmelt, mid snowmelt, and then late snowmelt. And this is on an elevational band. And so there are a couple of things that are worth pointing out here. Number one, in the lowest elevations and the highest elevations, this wildfire frequency is it's always low. And the reason for that is because there just isn't a lot of biomass there. At the low elevations in particular, there's very little biomass. These are, in a lot of the West, this is going to be grasslands or deserts. It's not to say that, I don't want to imply that those places would never burn, but there's just not a lot of fuel. So here's an example. This is Lancaster, California. It's up in the high deserts. It's a little bit wetter than like Victorville. Everybody been out to Victorville, Barstow? It's another example here. Like if you get east of Reno, like grasslands, desert, those kinds of environments, there's just not enough fuel here. You're not going to have a forest fire. But you have the largest change in frequency at this mid elevation. And if this was just done for the Sierra Nevada, this is exactly what we'd expect, because biomass and fuel levels peak in the mid elevations in the Sierra Nevada. That's where the range is the wettest. That's where we have the most forest growth. That's where we have the highest density forests. When you get up to the high elevations, then biomass starts to drop off. It's just too cold for extensive biomass to accumulate and so forth. And then in a lot of the Sierra Nevada, if once you get high enough, you even lose trees altogether. So snowpack dynamics in the mid elevations can tell you a lot about how the dynamics of wildfire in a particular season, and that's helpful. That gives us a basis to make prediction. And this is just some more information from this map, which again is highlighting the Sierra Nevada and largely forests like it. Much of the West, fire impact should expect to worsen. They were saying that in 2006, and that's what we've seen. Snowpack is important. And there was this detail in there that they had done work looking at fuels levels and whether prescribed burning and addressing fuels or accumulation of fuels would potentially be driving these dynamics. And they argue that that is not the main driver at this scale. Now, what I want to put this into context for you, because this is a really big area that we're talking about. It's the whole of the Western U.S. It's changes in climate. Their analysis suggests the strongest inference we can get out of this is that changes in the climate broadly are influencing our wildfire problem in the West. These authors, I really believe this, these authors wouldn't say that managing fuels is unimportant, or it doesn't have value, or it doesn't have a role in confronting this problem. But the big driver at this spatial scale certainly appears to be climate. There is one exception to this, summer and spring temperatures predicting when we're going to have a bad wildfire, and that's the adiabatic wind events, downslope wind events. These are some of the climatic conditions that are associated with the most damaging wildfires in California. So you may know these as Santa Ana winds, if you're from SoCal, or the Diablo winds if you're from up in the north, or even here the Santa Lucia winds. They're all the same thing. What's happening here is high pressure is accumulating out in the desert, out here, and that pushes warm, dry air downslope and then out towards the coast. And this does get channeled through tight landscape features like the Carquinez Straits in the San Francisco Bay Area, and then other things like that in different parts of the rest of the state. This is adiabatic winds or something. It's just broadly speaking, they happen in all kinds of environments. This example is from the Antarctic ice sheet. It's the same phenomenon, high pressure at higher elevations, pushing winds downslope. And the result is that you get warmer air, warm, dry air moving downslope. So if you've been through a Santa Ana wind event, and you probably have, I mean, we had a number of them here in SLO in the fall. It's part of life here. You know, it's like the desert heart of the West just comes inland to us. On those days I go outside and I look to the east and I feel like that's the Mojave Desert just coming here, you know, reaching out and punching me in the nose. These are hot. They're hot and dry winds. They can be extremely strong, you know, hurricane force at ridge lines. And under those circumstances, probably doesn't matter what the snowpack was doing, you know, whether it was a wet winter or not. It's if there's an ignition source, you're probably gonna have a problem. And especially here because everything's dried out in the fall anyway. So, you know, the Sonoma wildfires and this pre-Camp Fire, this was the wildfire tragedy that was on everybody's mind. This is it was a adiabatic wind event. You know, very strong winds, extremely damaging. The Sonoma area is going to be putting the pieces back together for a decade or more after this. Tragic, and extremely costly event. Not all wildfires are adiabatically driven, and not all of our coastal wildfires are adiabatically driven. Here's an example from Big Sur. This is not far away from here in SLO. 2008, the Basin Fire. That was a dry lightning storm fire, started in the spring. However, that particular year, the spring was notable for having been quite dry. So in some respects, we could predict that this could have occurred. Soberani's fire was 2016. It's actually right at the very end of the drought. We had had an average rainfall year prior to that fire, and the Soberani's fire was in June of 2016. The really big rainfall year was 2016-17. But we had an average rainfall year, and there was enough fuel, there was enough of everything, and it was dry enough. That was a very damaging fire also. I mean, the size of these fires kind of blows you away. 120,000 acres, 132,000 acres. The Soberani's fire burned. The Soberani's fire started in June, and it burned until it rained. It burned until September. It was still burning when we got the first rains. So, yeah, incredible costs too. I mean, these you know, loss of structures and stuff. You know, $120 million in direct attack expenses, $260 million in direct attack expenses. They're very, very costly events, even when they're mostly burning in wilderness. Okay, so my guess is that you're thinking about the different ways that we can have manage where are the different places in wildfire management where we can have an effect, where can we influence the severity of fire. And the past gives us some interesting insights into that. This is one of the better fire reconstructions. This is for redwood, so it's in coastal forests. And it'll take me a little bit to walk you through this, but it tells a really interesting story about California and how wildfire has changed here. So bear with me. You guys can see the cursor, right? So here I want to point out this period here. This is we're going back in time, and this is all reconstructed with scars, fire scars on trees. You can date the fire events. What you're seeing is, you know, the record becomes less well defined as you get further back in time. But generally, the pattern here is that prior to 1860 or so, 1820, you've got a really random scattering of fire occurrences. This fire is very frequent in this time, and it is, these are all different sites that you're seeing here, these letters here, these different sites, and they're on a gradient from east to west. Fires are very frequent, and they are not aligned. So one site is burning and another site is not. What this reflects are frequent fires that are relatively small. And this kind of pattern in fire dynamics is associated with indigenous burning practices. As a management strategy, it makes sense if you're managing your local acorn gathering, hunting grounds, other things that you do to maintain where you live, you burn when you need to. You know, you burn when you need to. You got a lot to do, you know, to survive, and fire is a useful tool for your priorities. But you know, you got a lot to do, so you burn when you need to. What happens here in the 1800s? There is a depopulation in California of indigenous people, and that's associated with the mission period and a genocide of native peoples in California. That led to a depopulation and a loss of this decentralized management. And fire is not being suppressed during that period, but what you start to see is that fires become aligned across all sites. So fire becomes less frequent, but what tends to happen is that when one site burns, they all burn. Oops, sorry. That is what we would expect when you have fire, when you have fewer fires overall, but their ignition is all associated with one event. It's associated with mining activity or a lightning strike or something like that. So they're not being suppressed. They're still much more frequent than current, and they're linked across the landscape. Now, the last phase that we have here is 1900 and beyond, and what you're seeing here, and this is not this is not a fluke. This isn't a problem with the data. There are no fires recorded in these places after about 1920 or so. That is despite that this record goes up to about 2000. That's not a mistake. That is actual data. There are no fires occurring in that period, at least through this record, with the exception of this one here in 1935 that burns one site, and that's corresponding with the period of fire suppression. So what you've got in a relatively short period of time, about 300 years, you go from fire is frequent and small, a widespread management tool, to the loss of that, and then progressive transition into widespread fire suppression. And if there was something that I was going to guess that would be on your mind before you came to class today, it would be, or something that I would expect you to be aware of, is that fire suppression has been a common tool, a common management strategy throughout the West, and it has created for us some serious problems. And this is just showing you that it's at least had an effect, even if whether you agree that it's a problem or not. So here's just some examples. This is terrible management. It's just a nightmare for fuels problems. This is a post clear cut that just was supposed to have multiple silvicultural interventions. It didn't. The agency ran out of money, and this thing overgrew into a very dense forest. This is bad. Here's another example. These places are really widespread, and oh man, are they a huge problem. They're just like, you see me just like rubbing my head. They're so expensive to clean up, and they're such a pain. They're just a nightmare. It's so hard to get this work done. But what you can do, you know, you can pile, you can doing something is better than nothing. Thinning here, piling, reduces fuels and could potentially, you know, improve wildfire conditions in that specific area. There's a lot of this land to treat, and so that's the hard part. It's like, how do you get it done? This is yeah, $3,000 to $10,000 per acre. It's like, you know, and the need is thousands and thousands of acres. So you're talking about massive expenses. We have big mountain to climb. Here's a picture of success. A pile of small stems. There are other factors. I'll spend more time talking about these as we go forward. We have a lot of other problems that are leading to fuels buildup in our forests, and I mentioned this in the video that I posted today. You know, fuels are living foliage as well as dead foliage and dead wood. And they have different effects on fire behavior and fire dynamics. But there are factors that are increasing them, like invasive species like sudden oak death and bark beetle. And then there's other stuff that doesn't get talked about as much, but other invasive plants, and Scotch broom, if you know about it, is one of the more problematic because it also tends to have a positive feedback on fire dynamics. And we have all kinds of sources of densification of our forests, including some of our adaptations to fire, like respawn. Okay, I'm gonna stop. I'm gonna, let's see.